Today, I am going to introduce you to the Central Asia Quaternary Fault Database. And this is a database that my colleagues from University of Tübingen and University of Montana, with lots of input from Central Asian colleagues, have been working on over the last few years. And I would like to share some of our results with you. As you can see, the link for the database is shown. Let me get the marker here. Okay. The link is shown here on the slide, and I will show this link again at the very end of the talk in case you didn't have a chance to write it down. But I highly encourage you to check out the website. It is online if you haven't done that already, and if you come across any problems, please get in touch with me and I would be more than happy to help you with that. Before we talk about Central Asian Fault Database, I just want to take a moment to talk about the impact of geologic hazards globally, but particularly in Central Asia. Now, what you're looking at here is the data from 2018, which shows the number of disasters by continents and the top 10 countries. And as you can see, all continents in 2018 suffered from natural disasters, but Asia suffered the most, as is shown here, with 45% of the disasters occurring in the continent of Asia. 80% of the deaths also occurred in Asia, and about 76% of people who were affected by natural disasters also were in Asia. Now, earthquakes were responsible for almost half of the total deaths that was observed in 2018. Now, you may ask, what makes Asia vulnerable to natural disasters? And there are many complex factors that contribute to that. And today I'm going to focus on just one factor, which is purely the tectonic setting of Asia. So Central Asia is located in the Alpine Himalayan belt. This belt is shown here in dashed black lines. And as you can see, this orogenic belt stretches from the Mediterranean Sea here to the west, all the way to the Pacific, covering a distance of over 16,000 kilometers across Eurasia. And much of Asia is located in this belt. This belt is also the location of 75% of all the earthquakes that have killed more than 10,000 people since 1900s. What you're looking at here, these circles are the locations of those significant earthquakes. The size of the circle indicates the total number of people who died due to that event. So the very small circles that you see here, such as this one, represent a total death of about 10,000 people, while the larger ones that you can see are the earthquakes that caused more than 300,000 deaths per event. And the color of the circle here also shows the magnitude of that earthquake. Now, the seismicity in the orogenic belt is actually driven by the ongoing collision of several tectonic plates, as shown here. So here we have the Indian plate that moves with respect to the Eurasian plate at a rate of about 40 to 50 millimeters per year, northwards, and also the Arabian plate and the African plate. And this plate collision has created a very complex zone of active deformation, as you can see here in the topography. And this zone of deformation is marked by intricate network of fault systems. These fault systems have hosted large earthquakes in the past and continue to pose hazards. Some of the recent examples of that are the 2005 Kashmir earthquake, the 2008 Wenchuan earthquake, and more recently in 2015, the Gorkha earthquake in Nepal. Now, we have created a Central Asia database to bring all the earthquake-related and fault-related parameters and information in one place. And we're going to focus mostly on the Himalaya-Tibet origin for the Central Asia database, which is shown here in the red box. So as you can see, we are highly motivated, and we have a lot of reasons to actually bring and centralize access to fault locations and characteristics and behaviors of faults that can be used for seismic hazard analysis and ultimately for reducing risk. So with that motivation, I'd like to take you through the roadmap for this talk. at the very beginning, we are going to talk about the database construction, how it was put together. And I will also share with you the user interface for this database, which includes an interactive map and a search tool that allows you to identify specific fault systems. And at the very end, I will talk about some of the database gaps and its completeness, and briefly share with you one application of the database that allows us to have a better understanding of the deformation pattern in Central Asia. So let's start with the database construction. So what you're looking at here is the stages that we took to construct the database. We first collected data from published literature and maps and catalogs. These data came from over 250 published manuscripts that were reviewed by us. And we also tapped into already existing catalogs, such as the Hima-Tibet map, and also for seismic catalogs, for instance, the USGS ANSS earthquake catalog. And once we have these catalogs, we basically we got all the fault traces, and we brought them into ArcMap software and used the which were used for, to populate tables that were created in a MySQL database using an open source web application, which is called PHP MyAdmin. And then using PHP scripting, we were able to work with the fault locations and bring attribute data from the tables for display in an open source web mapping application that is called OpenLayer. Now, the MySQL database actually contains more than 10,000 fault traces. At the moment, it contains more than 34,000 seismic events, and more than 100 of the faults that are in the database also come with attributes. We also have included landslide inventories, and I will talk a little bit more in this talk about those as well. So let's take a look at the user interface. And start with the interactive map. Now, when you go to the link that I provided earlier, you land on a page like this, and this is the main map interface of the database. It is interactive because this map allows you to zoom in and out, and it allows you to click on these red lines, which are the locations of quaternary faults. And if you hover your mouse over any of these faults, you will be able to get the name of the fault. And if you click on that fault, you will be able to go to a page that gives you more information about that specific fault. Now, users can also display earthquakes by choosing the earthquake layer. So the map layers are shown here on the right side. And if we choose the earthquake layer here on the right side, you see that you have a couple of options here. So for instance, you can choose the earthquake catalog that you're interested in displaying. Now, this could be a global catalog, or it could be a regional catalog. You can also view earthquakes by their magnitudes. So in this case, we show earthquakes, we sort earthquakes by magnitude being larger or smaller than 5. And also by earthquake depth. So those that are deeper than 70 kilometers and those that are shallower than that amount. And as you can see, in this case, the ANSS catalog gives us all the earthquakes that were recorded since 1900. And this is a lot of earthquakes. And you may not be able to see the structures anymore, but you can always zoom onto the map. So if we zoom in the Pamir, this is what you get. So you can see here the intense intermediate depth earthquakes that Lothar mentioned in his talk, which are about 90 to 250 kilometers deep, shown here in blue. And this is the seismicity that's related to the Hindu Kush and the southern part of the Pamir. And we also see shallow earthquakes that are focused along the northern margin of the Pamir in this area. You can also see some greenish events here, and these events are basically aftershocks of the Nura earthquake that happened quite recently. Now, if we go back to the display layer, we can also access landslide catalogs that have been published and are available digitally and freely for download. And at the moment, we have currently 6 catalogs that come from the USGS Science-Based Catalog. And these events are shown here in orange circles. And these are earthquake-induced landslides. And then we also have other catalogs that are shown here in dark gray, mostly for southern Kyrgyzstan and northern Tajikistan, that are all types of landslides and not just earthquake-induced ones. And if you go ahead and bring your cursor to any of these circles, you will be able to get the name for the landslide catalog. So in this case, for the Nepal earthquake, it's the Gorkha earthquake, the date of the earthquake, and also a link to download the data. And the same thing for non-earthquake induced landslide inventories. You're automatically taken to a page where you can download the data and use it freely. Now, another data layer that I want to bring your attention to, and this is one of our newest layers, is the Quaternary slip rates layer. And by choosing this layer, you are able to displace the locations of Quaternary slip rates measurements. So the circles that you see here mark those locations. The smaller circles correspond with a slip rate of less than 10 millimeters per year, and the larger circles correspond with a slip rate of more than 10 millimeters per year. And our intention is to also, in the near future, add the GPS rate so that the users can access and display both types of slip rates at the same time on the map. And this layer is also interactive. So if you click on any of these slip rates, you should be able to get more information about them. So for instance, if I click on this circle here, which is marked on the Darvaz Karakur fault in Tajikistan, the Quaternary slip rate shows up here, and the method that was used for that Quaternary slip rate, and the reference. So the people who actually measured that Quaternary rates. So as you may recall, I mentioned that the interactive map allows you to hover your mouse over certain faults, get the name of the fault. So in this case, we hover the mouse over the Chaman fault, and that fault turns black once you click on it, and then you're automatically taken to a page that looks like this. And this page summarizes the fault behavior and characteristics, and it's broken into 3 segments. So the very top part of the page here, we have the geographic characteristics of the fault, so things such as the level of exposure and where it is located. And then in the middle, we have the seismic characteristics for that fault, and that's where you will have access to published data on geodetic and quaternary slip rates, as well as any information on past earthquakes or paleo earthquakes and any trench studies that have been conducted there. And of course, you can see that there are comment sections as well, which describe the published literature on specific parameters. And at the very bottom, we have the structural characteristics, which focuses on geometric parameters for faults. And at the very end, you have the reference section, which gives you the link to articles that have been used to basically populate this page. So everything that you will read in this page is coming from a peer-reviewed article with the references listed here. So I want to take you now away from the map and to the search fault tool. This is a tool that we have developed that allows users to look for specific faults, either by entering the name of the fault in the top field, or by selecting the country or physiographic province. For instance, you can select from this link, this field, things such as the Tarim Basin. So if you want to display all the faults in the Tarim or surrounding the Tarim Basin, you can select that from the physiographic province. You could also limit your search by the seismic characteristics. So by entering different values for your geodetic and quaternary slip rates, or by selecting whether or not you're interested in faults that have historic earthquakes, they have geomorphic expressions, or have any paleoseismic studies associated with them, or by structural characteristics, which in this case is only the sense of movement for that fault. So let's just use an example here. So if I say I am interested in displaying all the faults that have historic earthquakes associated with them, you will get all those faults on the map. And again, this map is interactive, so you can still select these faults interactively. Also, the search results at the bottom of the page will tell you how many faults have been found and will give you a list of all the faults. So you can also go through that list and click on individual faults. And once you click on individual faults, you're taken to that information page that I showed earlier. So now let's take a look at the database completeness and data gaps. So I think the search tool is one of the best tools in this database that will allow us to really identify areas where future research are needed. So for instance, if I choose to displace all the faults with sense of movement, you can see that we get about 126 faults displayed on this map, and that's pretty much all the faults or the main faults that are included in the database. However, if I'm interested in displaying only faults that have reported and published quaternary slip rates, you see that that number is reduced to 32. So you can see that there are many structures, quaternary structures, that we still do not have any information concerning the quaternary slip rates. And that number is even smaller when I choose to look at geodetic slip rates. So again, you get the map, and as you can see, we have only 20 faults here that have published rates associated with them. Now, if I choose both quaternary and geodetic slip rates, you see that that number is about 19 faults. And this allows you to really see where the gap in information exists and where future investigations are actually needed. I should also mention that the database is an evolving tool. So there could be information that are missing from the database. And so if you come across a structure that maybe you know something about, maybe you have read a manuscript on, and you see that it is not included here or the information is missing, please always feel free to contact me, and I will do my best to incorporate that information in the database. So by no means it is a complete database, but we are working on it to make sure that it is up to date. I also want to point out the other links that you see up here. So we have a download button here, and the download button allows you to download shapefiles that you can use for your research or for the work that you're doing. You can always submit your feedback directly by completing a feedback form that's anonymous, or you can contact me directly. And there are also some other resources about the database, the publication that goes with the database, and some educational materials that you can use with your students and colleagues as well. So I'm going to just take a moment here, and this is going to be my last slide to show you basically how we can use the database to do further investigations. And in this case, I am very interested in these 19 faults that have both quaternary and GPS slip rates published for them. And what I've done is that I have basically put together a slip rate database which contains 57 slip rate pairs. So quaternary and GPS rates are being paired with one another, and that gives us 57 points that are shown here in black circles. And I have then combined that with the data set of Thatcher in 2009, which is a global data set of paired quaternary and GPS slip rates for specific faults. And then I have basically plotted them here to understand if there's any relationship between GPS slip rates and quaternary slip rates. Now, I did this to measure the dependency of quaternary slip rates on GPS slip rates. So on the x-axis, as you can see, we have the GPS slip rates given in millimeters per year. And on the y-axis, we have the quaternary slip rates given also in millimeters per year. Now, what we want to see how our y values basically change with changes in x values. And to identify the extent to which these rates relate to each other, we conduct a least square regression line, and we get an R-square value of 0.77 here for all the data combined. So the data from Central Asia as well as the global data sets of Thatcher. And this is really interesting. This is shown here in red line. And I've also plotted the reference line, which is shown here in black, where GPS and quaternary rates are equal to one another. And despite all the scatter of the data points that you see here, if you look a little bit more carefully, and if you consider the uncertainties within which these rates were reported, more or less, many of these data points actually agree with one another. And I should just say that this R square value of 0.71, which is shown on the red line, basically shows that a moderate percentage of the total variations in the quaternary slip rates, and that's about 71%, can be explained by the linear relationship that you see here between the reported GPS and the quaternary slip rates. And the remaining amount, that lower percentage of 29%, is basically remains kind of unexplained. So by doing analysis like this, you can quickly see what the outliers are, what those rates are associated with, what fault, and be able to go a little bit deeper into trying to understand why certain faults behave very differently when you compare their GPS versus their quaternary rates. And just to conclude here, so our open access database features a web-based interactive map and a database that is freely available to public. It has the search tool and a downloadable data set that allows you to have access to the data that I showed you today. And we are hoping that by making this database available to public, we can contribute to earthquake risk reduction and identify areas where further research is needed. In terms of what you can do, you can obviously access the database for visualizations, for looking up information, or simply downloading the data and using it however that fits you. We also encourage you to submit any new or missing published content through either the feedback form or contacting me directly. And we'd be happy to incorporate that into the database. And now that's the end of my talk. Thank you so much for your attention, and I would be happy to take any questions you have. Thank you.